So we're changing subjects. We're going a little bit more into robotics with our next presenter, Glen Berseth. Glen is an assistant professor, at the University of Montreal, a core academic member of MILA, as well as a SciFar AI chair and a co-director of the Robotics and Embodied AI Lab. There's a lot, sorry, a mouthful. His previous and current research has focused on solving sequential decision-making problems for real-world autonomous learning systems, or robots. The specific of his research has covered the areas of reinforcement, continual, meta, and hierarchical, I can't say that. Hierarchical learning, I'm sorry about that, and human-robot collaboration. In his work, Dr. Berseth has published at top venues across the disciplines of robotics, machine learning, and computer animation. Today, he'll talk about RL and robotics and design. So welcome, Glen.
Yeah, thank you very much for that great introduction. Good to meet you all today, and I also very encourage questions throughout the talk, so feel free to reach out if you have any particular questions going through it. So yeah, today, robots have actually been around for a long time. They're very useful tools. They're already helping us a lot in manufacturing. They're already helping us a lot in fulfillment, being able to package items and types of transportation already around the world. There we go. Yeah, and sorry. Truthfully, they've been around for a long time. So this is a robot from around almost 100 years ago. It's one of the first humanoid type robots. So robots aren't necessarily something new. But the developments that have happened in the last couple of years have been really like applying machine learning to make these robots, have more of the skills that at least people start to have, like easily interacting with the world, being able to use visual perception to be able to act and even arrange things and perform some tasks. So I'll be talking about some of these improvements today, and then some of the things that we can even improve on a bit more. So the parts that are a bit, hurdles these days is they still, like current methods that don't use as much machine learning, they are a little bit, they operate in very controlled environments. Maybe you've seen some of the pictures. We have a giant fulfillment warehouse. There's no people in there. There's cameras and sensor systems pretty much everywhere. If one sort of thing goes wrong, the entire building basically has to stop working. So these systems are still pretty brittle in some of the ways they're designed. And it often takes, a lot of prescriptive behaviors and engineers to come in, like program these robotic systems for a while. And this also introduces some other hurdles to using them. It means that before you even want to use a robot, you have to find a good robotics engineer that'll have any idea about how to use it before you start to maybe apply it to some of these other tasks. So how can we, at least, lower this bar significantly to be able to use automation more for the other types of tasks we're interested in? And there's a lot of benefits for this. I like to think of it as every person would have at least a bit more time to do whatever they want to do. I like to give at least this small example where, like, Einstein was working in a patent office. In his free time, he was doing mathematics because he loved mathematics and came up with things. Maybe it's this creative time that's where it's like the best time that we should try and give back to people, and that'll provide better benefits for society. You can also have a lot more agency for people as well, especially some older people. A lot of people are getting older these days. There's not as many younger people coming up to maybe take on some of the care that's going on. So robotics could help fill this area as well. But also I find that one of the tricky things, especially in terms of today's challenges, we're not very good at switching production. If we want to build an electronic car, minimum 10 years before you actually get to that point. You need a building that you plan. It takes about 5 years to construct it, 5 years of iteration time before you actually get one car, and probably a few more years of actually making it better. This, at least from my point of view, is a little bit sad in our ability to adapt to the changes that we really want to be able to make. And robotics could help make these types of adaptations much faster. And we could be a lot more efficient with space. They're being used already to help grow some food better. We can have more vertical farming type mechanisms where we don't have to specifically design all of our tools to work for people. Maybe, robots can fit into smaller spaces, not have the same constraints, and avoid a lot of waste and have much better reuse. So the challenge is to be able to get to some of these in terms of the machine learning that we have available today. Is we want and would need to be able to do all these more versatile robotic systems. This means that, basically everything that you deal with these days as well, maybe it's your first time visiting Mila, but you came in, you kind of knew that you'd sit down amongst the crowd. It's not very surprising how a chair works, even if it's a slightly different color than the other ones you visited throughout your life. But you want these systems to be as adaptive and not as restrictive in the things that they can do. But I also, like in my research, want to go beyond just providing them sort of like work well in different rooms or in different tasks, but give them really complex goals. Even things that we don't know how to do. And I like to at least get to the point, I want to ask a robot at some point, is there life on Mars? And now I can go back to my creative time, or maybe I'm thinking about other problems, and the robotic system will figure out how to go about, constructing, maybe an entire corporation that ends up learning how to launch rockets, how to do all the planning to be able to launch the actual system. In order there to actually figure out how to detect if there is any biological life on Mars, come back, give me the answer. Maybe quickly, at least in some time, but this would be the goal to try to get to. We want to be able to ask amongst ourselves and our systems questions that are more complex like these. And I'm actively doing a little bit of this as well in the Institut Courtois, where we're designing an automated, basically chemistry system to be able to just have it so that the scientists there can ask questions. I want to be able to produce this type of system. We can automate most of the manual process, maybe even some of the decision making. Okay, so getting into the tools that I've been using in this area and that I believe are really promising in here too, because they help solve what is basically a really complex sequential decision-making problem. We need to figure out how to make these things very flexible in the way they plan. So reinforcement learning is a great tool in this area because it allows agents to learn how to plan just from interacting. All we have to do is give them a little bit of an embodiment. They can go out and collect a bunch of data, figure out how to do a better job at figuring out whether there's life on Mars over time. And it's nice because it encapsulates most of the machine learning system all in like this general paradigm. And as long as we can figure out how to adapt it to the real world problems better, we get to make use of this kind of simple paradigm that results in a great learning system. So basically you've got for reinforcement learning, you got an agent that goes out, collects some data in the world, it records its state information. The reward signal, which is usually what we use to describe, the behavior we want the agent to actually achieve. And then it learns to take actions in the world and slowly improve these actions over time. And these more recent days, the deep part of deep reinforcement learning has been very helpful. Now we can just pile into the robot or agent a lot of extra information, whatever it could be that's useful. And whenever it's going out trying to decide actions, now it can learn from the image observations that it's given or any other kind of sensory observation. In this state, now that I can identify better, this is the better action I should take. Update the overall network parameters such that the next time I visit this state, I at least repeat the action that was, overall looked better according to my reward function. So slowly over time can update this deep learning model to produce a lot of sequences of actions for planning that would result in higher value models towards those things for like being able to find life on Mars as an example for a goal. So this is a nice paradigm, but applying this in practice is where it starts to at least, expose a few cracks because we want it to be as adaptable as people are. But that means that it needs to be able to generalize better, and some parts of the system don't generalize as well. So what is sort of missing from this overall paradigm, and that we're like learning a little bit more from these days, is really though that we still don't have enough data. So we've been seeing probably that language models have been able to be pretty successful because they more or less borrow a lot of the good information from the internet. We've been kind of very nicely piling the 20 years of all of our best thoughts into the internet. Now we can create a system from that that's somewhat intelligent. So maybe we just need to spend the next 20 years collecting a bunch of data. Basically, you could record people, the things that they're doing to show that they're actually doing things that are smartly, and then be able to train a robot system from this. And it should be able to generalize. And it's also important to have like good diversity. So I'd want like data from everyone in the room really nicely to see how you all perform tasks differently. And that gives it this sort of more adaptive behavior as well when you've got that much diversity. And then what do you do if an agent, I guess, previous more like language model based thing is collect a whole bunch of data, freeze that. What if you run into a novel situation, which we do every single day? Just apply reinforcement learning. It's the literal system for interact with your world, increase your reward function. and just keep going from there forth. So I'll talk about a few ways to be able to apply this to a couple of different applied tasks. So the last part is like now just trying to get this to work more in the real world. So here's a video from one of the earlier DARPA tasks of working on getting humanoid robots to do things that are more or less related to being able to recover from some disaster situations. You can train in simulation, but those aren't always well designed for certain tasks. It takes a lot of work to make a simulation too. So in some ways, the difficulty we go in creating the simulator, we might as well just work on collecting more ground truth data that's actual fact in the real world. And then we can use that to build on these systems. And we just need to figure out how to incorporate this data into these systems. So the last kind of interesting caveat is we're talking a lot about data. And when we're doing large language models in those cases, there was a process where they skimmed the best data from the internet. So we also need to be more kind of considerate about what that kind of data should be. So in this case, is it enough to collect any type of interaction data? You can think of a robot arm here isn't going to know much about navigation. A car, isn't going to know much about actually manipulating things in the world. And this amoeba here is a great example. It's kind of got a very small world, doesn't have many tasks. So it's not going to have a really large breadth of things it's going to have to learn. So there won't be a lot of great information inside of the data set. So intelligence also has, some kind of strong connections to the morphology of the actual agent that's doing these things. So these are not great examples. We want to get back to this Einstein type robot that, can sit, do math, and most of the other things that people would probably be able to do as well. There's also sort of a few fun caveats where it's not just a humanoid robot. Many of them need to also have some of the important features. I kind of like to point out this one for Boston Dynamics. It's a great biped, but it has no hands. It's got basically fists. So I don't expect it to cook me dinner nicely or anything like that. You still need portions of this full system in order to collect all the data that we would like. So can we get a robot to start to do most of the tasks a person could? All right, so here I'll talk about one of my first, or at least the first project I'll talk about today, is about trying to kind of drill down more onto two of the concepts here. We want to collect more data, and we want a system that both navigates and manipulates stuff in the world. And in this case, there's basically no supervision that's implied in this project or used from the people. As long as we make this robotic system, we put it down in some room, over time, it just learns to clean the room. It takes about a day for it to learn how to train. And then, so some of the methods that are used here is basically, you can take this now system, and the morphology is fairly important. Start by training it to grasp some objects. So we basically put it in the room, put a pile of things in front of it that it can learn to grasp, and basically give it some time just to practice. It doesn't drive around as much. And then once it starts to get some grasping ability, then we just kind of turn on the navigation part for the overall agent. And now it can actually go around, grasp things, learn up how to clean around in the room. And what really helps in this case is actually being able to allow it to train here in open space. So there's some hangups for applying robotics. Actually, if we just change the task a little bit such that it doesn't have a few of these resetting issues, now it can go along collecting and make some progress towards collecting this internet amount scale of data that we would want to train these agents from. So the reason why this is also nice is machine learning systems, as long as you give them more time or data, they tend to beat out a lot of expertly designed systems. So here, this is just, the robot after it's trained for a day inside of this room on its own can run around in the room, clean up all of these little, in this case, they're balled up socks that were used as basically trash that's inside of the room. And if you give it enough time, we basically grabbed a version of a controller that was the best expertly created thing we could think of, spent a couple of weeks making it. But if it took us 3 weeks to make the scripted controller and 2 days to train the learning one. So if we get to this scale part, then we already start to get the better advantages from learning. And we can just take this robot and put it in any other room without having to do any more kind of crafting of a sensor system, and it can still keep learning to do this task there as well. Okay, so we've got some good components where we're learning from large scale data already, but we also want to learn some more useful structure. And this is the part where we want to be able to generalize better. So that previous project learned in a room from scratch, but what can we transfer? It'd be nice to use the data that was also learned there and use it for other tasks, where we can automate this process to be able to collect more data, but it's also good to find better structured policies. And one way of thinking about doing this is you could make like more of a goal condition policy where I would, give this picture, sorry, hopefully you can see this on the right to my robot, please clean my room. This is the current state. I want it to look like this, which is much better, much more clean. And now you can have it just generalized to different rooms and give it different pictures and have it be able to clean. And you want to be able to like learn this causal model across these different goals. And you can do this using machine learning and deep reinforcement learning as well. Some of the caveats are you do need to generate some additional goal data. So if you don't happen to have access to a bunch of clean and dirty rooms, you can use a model to generate basically clean and dirty rooms. So collect a bunch of data from the internet. Now you can generate what looks like clean and dirty, feed those into the policy, and then put it in an actual room. And you just need to provide one clean picture of your room. Hopefully everyone in here at least has one picture of the room when it was clean, and then you can use that to be able to, with this agent to help it clean. Okay, so one of the last challenges is dealing with the problem of, when you collect data on a robot, even on the one was in here, it was on that specific robot. We'd like to be able to make better use of our data so that's not specific to one individual robot. I'd like to be able to like train a robot arm and then also train a different robot that can just walk around, glue those two policies together, and it should basically be able to learn from that. You've collected a lot of data on how to solve these different tasks. You shouldn't have to collect wholly new data on the combination of these two robots. So this is the next work that I'll talk about. We're going to learn, via some large scale interaction, how to train a policy, one single policy that basically figures out how to control all of these different morphologies in the simulation. And we don't need to provide much information basically to tell it what the morphology is. So from here, we're basically going to use a transformer model, and we actually construct it basically such that you can send in a bit of information to the model, which is kind of a really rough approximation for what a description of the actual robot is. Kind of something as simple as, it has two arms, it has two legs. That's all the information you need to know. Now you can go perform the task. So this has been really helpful because now it allows us to generalize across these different robots. So if I have a different robot or a different agent, I can give a bit of a description and include the data from that robot into this model as well. And this also gives us some great progress in terms of generalization. So if we hold out a bunch of different robot designs and then ask them to, in this case, ask them to do some generalization to these new ones, we get fairly good performance in terms of how well it still gets reward on these tasks for an entirely different morphology for an agent. So it could have like less arms, more legs, different joints, and it's still able to map to these types of generalizations. And in this particular work, we were trying to get rid of having to assume a lot of the information about morphology, because usually in a robot system, you have to have an engineer again, carefully program the actual design of the robot, where the links are, their lengths, their weight, provide that to the model. In this case, we're able to train the network and just feed in a version of a state representation. And then from that, it learns just that, actually how to infer what the morphology is and how to control the agent from that. So the only thing we really end up having to do is a bit of a tokenization of the state. We feed this in as if it's a sentence, and then the ordering and description basically allows it, okay, this must be the ant robot with 4 legs or 5 legs this time, now that it has some extra joints than what it had from before. And we're also starting to see, if we at least look at some of the stuff in the transformer model, it's learning a very sparse attention. So it is figuring out like which joints actually connect to other joints, which ones you can ignore, and which ones end up being important for actual actions that come out of the model. So it's learning essentially, it's learning that wiring system for the robot's design internally. Okay, So the last part on this is I'm going to talk a little bit about task generalization. So I talked a bit about goal conditioning. We want to think about how to give tasks to our systems, and these perform a lot of planning. So in this case, I talked about this goal conditioning problem, but I asked the robot in that example, clean the room. There happens to be a window in the back of this room. Does this mean the robot should also go outside, reconfigure the entire planet back to the time that was in that image? Because that is what I told the robot at the time. This is not what I meant. At least I'm pretty sure it's not what I meant. But it was pretty late for that deadline. But basically, it could be really nice to be able to replace some of these things with text. Images tend to over-specify problems. Text tends to under-specify the problem, but that gives us more freedom to do things. So if we can use more natural goals, we can just say like, go clean the kitchen, things like that. I don't need to provide an image now, which is nice because we can get away with ever having to have our room clean now, as long as someone else cleaned their room. And then now we can reuse this data. So we want to get now to tasks that we don't know much about. So this is helpful because like a large portion of things we apply machine learning to is things we already know how to do. But I'll go through this a bit quickly. We want to get to the point where like we want to ask a system, design a more efficient battery, or one of those questions, is there life on Mars? More general goals. So in some recent work, I've now been like applying this overall to being able to find really high, like really useful molecules, either for drug discovery in some ways, or also for manufacturing design. And this becomes this version of actually specifying a problem. In this case, we're going to rely on text a lot more too. We're going to take the original, basically description, which is usually graphical over here, sorry. For the actual molecule, we can convert those into text thanks to a couple of new libraries, which means we can try to take advantage of the text that's available on the internet or these large models, and then be able to use transformers to be able to train a good text model to perform RL and use the big hammer that is deep RL, basically, consume a lot of data, perform a giant search over all the possible combinations of molecules to try and find better ones. And really what we tried to pull on a lot in this project is taking advantage of data sets that use text. And there are some large ones for molecules as well. In particular, we targeted like molecular docking and a couple of other tasks for being able to do different types of molecule design. And the results that we get, I guess, if you're more familiar with, there's also two kind of grammars that you can use to describe a molecule in text. So we do some comparisons between those as well to see how well these grammars mesh basically with search and deep reinforcement learning, the tools that are available. So basically, it's a combination of many things. We've got selfies and some grammars for trying to figure out good policy architectures in this new type of design space. And how big we need to have these models to be able to consume these large amounts of data, and then also do some exploration according to different reward functions. So we find that in terms for one kind of group of tasks that is more diverse, we find that using the transformer models that we train, we pre-train them on language and some molecular data, and then we use reinforcement learning to improve the performance, work really well on a lot of these tasks. For some of the docking tasks, the transformers don't perform as well. We're still investigating that one. We think the docking tasks are really specific and not as related to the data sets that we have available from basically molecules as text. So that's sort of a future area of research. So this is sort of where we study different data sets and how much they increase performance. And interestingly, the ChemBL data set ends up being fairly helpful for being able to train these models, partly because that data set is a bit more diverse. So we've got these giant data sets of different zinc molecules that go into the billions of basically points, but it's not a very diverse data set. So we need that diversity back again to really take advantage of these large models. Need diversity, need multitask information. Okay, so there's some connections between these, but maybe I'll go through and pass on these for now, just so we can ask some other questions. I'm also I'm designing my lab as well to kind of hammer in more on this multitask learning part. A bunch of data from a bunch of different robots, create one model that'll control pretty much them all. Great, and then basically that's the overall talk. And if you have some additional questions, I'd be happy to answer them.
Thank you very much, Glen. Any questions in the room or online? No, but thank you for the reference to, I don't know if it was intentional, but Lord of the Rings, to one ring to rule them all.
It's a good ring. I
It's a good
swear.
ring. I would hope so. Thank you, Glenn, so much for your presentation. For the robotics summer school, yeah, maybe you want to say a few words happening in 2 weeks, I believe.
Yes, I mean, for those that are interested, we're organizing a robotics summer school. The aim is to like help kind of two directions. People that are more machine learning people get more familiar with robotics, and people that are more robotics people get more familiar with machine learning. And then together, we could help, make more progress, learn some more about these new skills, and be able to grow some of the process of even collecting this data and advancing robotics and automation for the future.